Everyone, how are you? My name is Amit. I'm a data science team lead at K Health, as most of you maybe know it. And today we're going to talk about data-driven primary and urgent care. And what we're actually going to do is take a stroll down memory lane and kind of see how we developed our first models and what were the challenges, and then I'll tell you a little bit about how we do things nowadays, which is so much cooler and much more efficient. Okay, so a little bit about myself. I have a BSc in computer science and physics from Tel Aviv University. I finished my BSc at 2012, and during my studies, I had a small project, like a summer internship, where I studied like the metaphysical state of monolayer sheets under different pH levels. And this opened the gate for me to kind of get more interested in the biology world. So I moved on to do an MSc and a PhD in biology here in Tel Aviv as well. And both my MSc and PhD were computational biology. I really tried to do experimental work, but I'm just not cut out for it. So I started doing experiments, and then I realized I'm better off just writing the analysis for the experiments. So for my MSc, I developed a tool that can analyze 2D high resolution microscopy images and find spatial differences between protein organization in a healthy and sick brain. And for my PhD, I studied genetic sequences, and I wanted to find anomalies in protein translation that can create new proteins that are otherwise unknown. So both my MSc and PhD were around machine learning and data science. I just didn't realize it. And then 2018 came, and I heard about this program, Y Data, and I looked at the syllabus and I said, kind of sounds like stuff I'm doing, but I don't really know the lingo. So I decided to sign up. It was the first batch. It was amazing and awesome. And to me, it was the gateway to starting my career. So you should all be happy that you're here. And right after Y Data, I started working at K. I started as a senior data scientist, and I was working on developing classifiers, working directly on the key product that the company markets. And today I'm a data science team lead, still working on the same model, just on a broader scale. So what does K do? Basically, our motto is we utilize the power of data to build new and improved healthcare systems. We don't want to just be another healthcare provider or just another HMO. We actually want to be better than doctors. We have the ability to utilize the massive amounts of data that we have and the interactions that we create between patients and AI, and the doctors and AI, and the patients and the doctor in our platform, and we can learn from it and improve and create a very good diagnostic system. So what does the app look like? We have an app that is marketed to users, to patients. The app is relevant to people who feel sick. They want to find out what they have. So they start having a medical health dialogue about their symptoms, a little bit about other features that relates to them. And eventually, after the dialogue, the system gives a differential diagnosis. It gives a prediction of what are the possible conditions and the probabilities of each condition. And we also give recommendations and information about what you can do regarding the conditions that you see for each condition. So maybe you can take over-the-counter medication. Maybe you should seek medical help. Maybe under specific conditions, you should seek medical help. And everything is data-driven and based on people like me. So I'm giving you a prediction based on people like you, what I saw, what I learned. If you want, you can move on to speak with a medical doctor. So this is also text-based. It's a chat between the patient and the doctor, and you can get prescriptions, referrals, or whatever you might need from the doctor. And this is also data that we collect and then we can use. So we're going to talk about the Diagnostic Tool. And the Diagnostic Tool is what drives the user-facing product, the product that helps give the diagnosis to people searching to know what they have. And the cool thing about K is that one of the business KPIs is classifier accuracy. So this means that the data group is the center, one of the center things in the company, and we work closely with the product and we work closely with the business to create the solutions and to create the products that we later market. The diagnostic tool is kind of divided into two parts. We have the patient intake tool, which is where you report what you're feeling. You start the health dialogue saying, oh, I have a headache, or I want to know if I might have COVID because I heard that there's COVID around me and I need to know if I'm at risk. And then you have a conversation. It's an automatic conversation. We ask you very targeted questions, and it's not a very long conversation. We don't ask you all the symptoms in the world because, I mean, you won't make it. So we're trying to be very, very focused and collect only the data that is relevant for us to make a diagnosis. And then we have the information revolution result, which is the actual prediction, the differential diagnosis. And this is what the classifier thinks that is most likely your condition. And we have the information pages, which are also based on data. So what prescription drugs are given, what is the expected time for recovery, symptoms that are very common in these conditions, and things like that. So that's the diagnostic pipeline. So as I said, we're gonna talk a little bit about K's history and how it started. So we have a lot of data, we got a lot of data, and now we need to build a diagnostic classifier, the first diagnostic classifier. So this is an example of how the data kind of looks like. It's a data that we got from one of the biggest HMOs in Israel, millions and millions of what we call electronic health records. An electronic health record is like a file that you have with many fields, a text field, fields specifying parameters about the patient, his age, his gender, maybe medication he takes on a normal basis, maybe some background conditions that he might have. This record can also have results from lab tests that the patient got, or maybe a physical examination that a doctor did during the in-person clinic meeting. And we need to take all this and get features. So some features maybe are easier to get, like the age, the gender. It's something that's supposed to be kind of structured, but the main core of the electronic health record is the text. And we need to take only relevant features from the text. And the text is complex, as you might know. I don't know if you've already had those courses yet, but learning features from text is not easy because doctors write them and they write whatever they want, and they write in acronyms and they have typos, and they don't write everything that they wanted to write. And they sometimes use Latin terminology, and they sometimes use English terminology, and some of them maybe write in Russian. And we also need to learn context. So if we have like headache in the past week, mild bed-like radiates off the back of the neck, mostly in the evenings, we need to understand that all of these things relate to the headache. So we need to understand that these are attributes of a specific feature. We need to know denies fever or throat is something that is negative related to the positive symptoms that the patient reports. And to top it all off, everything is in Hebrew, and our system works in English. So the first thing that was done in K was building an NLP tool that can read, that can learn to read those EHR, those big text inputs, and build what we call the structured knowledge, or our feature space, our feature store, which will later be our input features for a classifier model. And the knowledge base is very complex, and it's hierarchical, and you can imagine all the weird things that can happen there. And eventually, from analyzing millions of records, we were left with about 25,000 features, which is a lot. Next. It's kind of an embedding tool, doesn't translate. We actually take the text and extract a single feature. So we don't take the text and translate it into English, and from that we embed. We'll get to that. Okay, so the next step, learn to fly. We have features. Yay, we're very happy. I forgot to mention that part of the EHR is a diagnosis. So we have the label. This is what we want to predict. We have the features, and now we need to start creating a model, learning a model, and working in such a huge data space with millions of records, tens of thousands of features, a lot of labels. So this is multi-class, hundreds of labels. We have a lot of noise in this data. So first off, we need to understand how we clean it. How do we lose records that are irrelevant? For example, records that are very, very wrong. So diagnosis of pregnancy when the gender is male. This doesn't make sense. We need to take it off. We also might have some labels that are just wrong and we don't know it. Not all the features are relevant. A lot of the features are correlated. A lot of the features are synonyms. We weren't able to learn the synonyms very well. So there's a lot of work to be done there. And lucky us, we have domain experts working at K. The domain experts are doctors, and they can look at the features and tell us, okay, this and this is exactly the same. You can just make it one feature. They can tell us, you can't ask, you can't use this feature because this is a physical exam. The user can't do it, so you just have to eliminate it. And then we have a lot of data analysis work to find all the interaction, all the feature engineering, interesting feature engineering that we need to do based on those features. And we ended up with a database that still has millions of records, but is limited to about 4,000 features and roughly 300 classes, which is quite good. Yeah. You mean how many of the features the doctors said this you can use and this you can't use? A couple of thousand, I guess. They didn't go over the entire 20,000. We cleaned out like features that are very sparse, that were not highly represented in any class. We also didn't use all of the diagnosis. So some of the diagnosis, we just can't claim to diagnose. It requires tests. It's like severe diagnosis and stuff like that. So this also narrows the space as well. Yeah.
Is there other class like
no.
Closed,
The baseline is that whoever comes to us has something, and we need to give him something. We don't say, okay, we don't know what you have. Maybe you have something else. Maybe you're healthy. This is not the way that we work. This is why we aim to be as broad as we can. We don't want to be in a situation where we don't know what to tell the user. But then again, we are still under the hat of what we call the primary care, the urgent care. We will not treat like chronic disease handling diabetes using this tool. Okay, so yeah, so we have to train the model. Again, the millions of entry points, thousands of features. It's a sparse matrix. We have about 300 diagnoses, 300 labels, very, very imbalanced. Okay, we have some diagnoses that take up a third of the database. We have some diagnoses that have maybe 200 entries in the entire data space. And also we have some labels or groups that are slightly overlapping. So some conditions are very, very similar. Pneumonia and flu kind of have similar symptoms. They might have something that differentiates them, but you might be easily confused. And under all these constraints, we need to work and build a classifier. And once we have a classifier, we need to evaluate it. How do we know if it's good? So if you think about like the simple problems, you have the database, you have the labels, it's imbalanced, and you know that you can calculate something and you say that if it's above, I don't know, some percentage, it's better than random, okay? Here it's a little bit more complicated. We're inside the medical scope. So we have some guidelines for the model, what the model must do. So we can't miss alerting conditions. If this patient probably has appendicitis, we need to catch it because this is a serious condition, you can't miss it. On the other hand, we don't want to alarm the user needlessly. So if he has abdominal pain, it doesn't necessarily mean that he has appendicitis. We don't just want to say appendicitis for every abdominal pain. And basically, we can be wrong, and specifically, you can be stupidly wrong. So if a user is having a conversation regarding some ear complaints and we say, well, okay, you're on your period, that's not very good. This is very, very stupid mistake. And then again, we ask, okay, so what's the precision level that we need to get to, or the recall level that we need to get to? Maybe we should use F1. How do we handle those severe conditions that we shouldn't miss but can't just falsely alert? And how do we handle the fact that some conditions are very, very common and take up most of the data and they overpower our other conditions? And I mean, we were kind of like, what's good enough? How do we know that this model is good enough to meet patients? And the answer was, we don't know. So in comes the medical experts. What the medical experts can do is look at population statistics that we can provide. So we take our model and we predict on the evaluation set that we kept aside. And we give them statistics on how the population look when we have true negative and true positives for each condition, for each class. And then we can also show the population statistics of the false positives and the false negatives. And we can already see, we can start doing error analysis. We can already see that, oh, this is a false positive because in all of the false positives for this condition, for, I don't know, food poisoning, the starting time for the symptoms are very, very long. It doesn't make sense. So you can just, when the starting time is long, just don't say food poisoning and then you're fine. And we find all kind of hacks and things like that. And basically what happened is the doctors did manual error analysis on the cases where we did wrong, trying to figure out why did we do it wrong and how can we fix it. The guideline for good enough was no showstoppers in the cases. What does no showstoppers mean? Whatever the doctors decided on. Of course, this is very, very biased by the doctor that does the manual error analysis. And it's not just one doctor because it's hundreds of cases. So it was a couple of doctors and there was disagreement. So we have doctors that are coming from the ER and doctors that are coming from the community clinics, and we have infectious disease experts, and everybody says, okay, well, this is not a showstopper. It's not that bad that you say this. But this one says, no, it's really bad. You can't say it. So a lot of opinions, a lot of mess, takes a lot of time, and basically, this is not sustainable. But it was good enough for us when we first started off because we didn't know how to do things differently. So now the model is out. and we start monitoring the model in the real world. And what we see is everything we assumed was wrong. Not everything, but a lot of things. For example, the distribution of conditions that we have in our data doesn't match the distribution conditions in the wild. So we have in our data like very severe cases of head traumas and appendicitis and other things that if they happen to you, you would probably just go to the doctor or the hospital, you won't open the app for it. So we have a shift in the labels. One major issue that we have is that we learn data from EHRs coming from an Israeli HMO, but the main audience that we have are US app users. And this not only shifts the way that the user interacts with the app, but it also creates a shift in epidemiology because, for example, Lyme disease, which is a disease that doesn't exist in Israel, it's very, very common in specific areas in the US, and we just didn't diagnose it. We didn't have it. So we had missing labels. We had cultural changes. So Israeli patients maybe represent or say their symptoms differently than what the US users say it. And one of the biggest issues is that we learn data from what the doctor wrote in the note, and now we are trying to infer about self-reported, user-reported symptoms. So the doctor might not write everything that you say in the clinic. He will only write what is relevant for what he thinks is the diagnosis. So we can see that the number of features, average features per case that we have in the training data was around 4, while from the app, the number of symptoms that a user reports is about 20, 22 features. It's a big shift. It creates a lot of problems in prediction, and it can affect the confidence of the model. So it started out very optimistic and we were very happy, and we realized that there's a lot that we need to still learn and figure out and improve. We need to be in a constant improving loop for the diagnostic classifier on each class, learning new classes that were otherwise unknown to us, and understanding how we interact with the data shifts that we meet in the wild. So then we came to the new age of diagnostic modeling, and it's more than just changing the model that we use or changing the data that we use. It's actually changing the entire approach of how we model the data, how we evaluate the data, and how we present the data in the real world. So now we have our app data, not just the EHR data. The data, the model was live, millions of users, millions of chats. We have a lot of data. And what's even cooler is that, as I said before, after the automatic chat, the user can choose to talk to a doctor, and the doctor later puts in a diagnosis. So we also have labels for the data that we create for ourselves. So now we don't need to do, specifically for the app data, we don't need to do any complex NLP work to extract features because the features are built in as we collected them. The diagnosis is just a field that we take from the dialogue with the physician. So we can take this data and again, train a model. And now we feel maybe more confident about the model because the features are representing more the population, and the diagnosis are shouldn't be missing and should be representing the diagnosis distribution in the wild. So hopefully this model should just be better. It just should fit more. So now we need to evaluate again. And we have the same guidelines. We don't want to miss anything. We don't want to learn. We don't want to be wrong. We need to know if this model is better than the old model. So again, how do we know that this model is better? Because we have hundreds of classes and we are training a model on hundreds of classes. So it might be better on some classes. It might not be better on others. We have new classes that we don't know if we are just good at them because they're new. We have nothing to compare to. And we can just say, okay, if the new precision is bigger than the old one, if the new recall is bigger than the old one, stuff like that. But then again, we have the same question. What do we do with severe conditions? What do we do with highly common conditions? How do we know that the model is better? Again, we don't know. We have no idea how to answer this question effectively and confidently and agreed upon by everyone. So what do? Manual evaluation. Again, and this is the point that we said, okay, no, this cannot be the thing that we do. It's not sustainable. We live in a world that is highly dynamic. We have new conditions coming in. We have populations changing. We are entering even new states in the US. They present a new population. We cannot keep this up by maintaining a high frequency of updating our models and being accurate. So that's it. No more manual evaluation of the errors that we have on the model after we train them, blah, blah, blah. This will not happen. What will happen is building a new evaluation pipeline that would be automatic. What do I mean automatic? We don't need manual inspection of errors there because it is built in a way that would be good enough to represent the performance of models compared to other models. It will be good enough to comprehend the opinions of doctors on specific conditions, and it would be good enough to represent the entire population that we are trying to diagnose. So the three main things that we wanted to make sure that this evaluation framework would have is one, the data would represent the population, as I said. Two, we need to create a trust between us, the data scientists, and the doctors that hold the medical integrity of saying, okay, yes, this model is good. So we need to build this trust by letting them understand why this evaluation framework and why the results that we are showing from the evaluation framework represent what, if a model is good enough or better than another model. And finally, we need that the output from the evaluation pipeline or evaluation model to be as explainable as possible, easy to understand, because there are other stakeholders in the company that when I come and say, okay, I have a model, this is good, and the CEO comes and tells me why is it good? How can you tell me this is good? And I need to be able to explain it by very simple metrics, single numbers, and not like whole and confusion metrics that are 300 and 300 and no one can understand what's going on. Yeah.
How many data points do you have it?
Mm-hmm. So yeah, we could have several. Yeah. Yeah. So the question was, how many data points do we have per patient? So we could have several data points per patient. We could have like a medical journey. The diagnostic model that I'm presenting here is meant for acute cases. So these are cases where you come into the clinic and you get a diagnosis. So you don't need extra visits or maintenance of the conditions. Yeah. Okay, so how do we build such an evaluation pipeline, which is so good and so awesome? We start by sampling, of course. If we take like a single case from the app and we take out the features and then we show it to the doctors, as I said before, when we did the manual error analysis, the doctors would get the case, look at what the classifier said. One doctor would say, oh, that's okay. One doctor would say, that's not okay. This should be here. This shouldn't be here. Okay, I'm taking a case, giving it to several doctors. Tell me what you think is in the case. Tell me what the diagnosis should be. I collect multiple opinions for the diagnosis, and then I just have some kind of agreement measure about each of the diagnoses that was presented by this group of doctors. And I can do this for a lot of cases. I can sample enough cases to represent my population. And these are hundreds of cases. Okay, it's not a small data set. And I give each case to multiple doctors. They don't have to be the same doctors. just need to be enough opinions. And for each case, I can have this level of agreement. And when I have these different level of agreements, I can find those cases and those diagnoses where I have full agreement. If I have a case where all the doctors that I gave them to gave a specific diagnosis, I know that my classifier can't go wrong there. So if I have full agreement, I have a classifier, I have a data set that suffices the don't look stupid. Like, I have to get this. If I don't get this, my classifier isn't good. If I don't have full agreement, partial agreement, I can calculate any metric I want, any metric that is relevant based on agreement. So even recall can be calculated with penalties based on agreement calculated from this cohort. So now we have two measures. One is based on full agreement. I need to succeed. I will never release a model that doesn't succeed on all these cases. And then I have another level of agreement where I calculate any metric, and I have a couple of metrics there. And whenever I compare one model to another, I need to make sure that I crank up the numbers, that I give better results from this data. How does it help build the trust? The doctors are the one annotating. They saw the cases. They know what they represent. If at any point they feel that there is lack of representation of any condition or any situation, we just add more cases to this data set. The doctors know that if they don't do a good job in labeling, they can only blame themselves, because we later evaluate this automatically. This data set is dynamic. It takes a lot of time to do it. We aim to do it once, but the world is dynamic. COVID is presented. We need to add more cases to this data set and do this process again. So we won't do this process every month. We won't do this process every model, but when will we do this process? When we find a data shift in our real world representation of the data. This is when we need to reevaluate the evaluation pipeline and introduce changes. And again, once we have this pipeline working fast enough, it becomes more efficient and becomes easier to get this flow running and building these data sets. So that's our data science cycle. Okay, we have the normal cycle of collecting the data, having a data cohort, and then building features, looking at the labels, evening out the data if we need to, sampling, upsampling, downsampling, whatever. We choose a model and we train the model. We do error analysis in the means of we had train set and validation set. We did cross-validation. We come to a conclusion that, okay, we trained a model. This model needs to be tested. This model is good. I want to release this model. I want to make this model, put it in production. Then I take this model and I run it through this evaluation framework. The evaluation framework gives me numbers. It could be 6 numbers, 6 different numbers, each representing one level of agreement or one level of guidelines that I need to look up to. And then I have my decision-making process. As I said before, one trivial decision is if I don't pass on all those full agreement cases, this model doesn't need the wild. If I don't improve in the metrics of physician agreement, this model doesn't go into the wild. If I do, if I pass all my thresholds, if I pass all my tests and everything is good, all the boxes are checked, I go and deploy. That's it. No manual error analysis. I know that there are errors. I know that I'm not always right. This is a statistical model. Everybody understands it. But since we built the evaluation framework to be in a way that suffices our integrity, we don't need to look at it anymore manually. Okay, so as I said, like 10 times, the importance of this evaluation is that it helps us get responsibility and integrity. So we have the don't miss alerting cases, don't alarm unnecessarily, don't be wrong, but we have an added value of we can be better than the average doctor. Because think of it like going to like several specialists to get multiple opinions. You would eventually get the better treatment because you get all the information that you need to make an informed decision. So this is kind of like what we're trying to do. We are getting a lot of opinions. We have a lot of information, and we utilize this to actually be better than what the average doctor or what a single doctor can give you. The other side of the fence is what happens after we deploy, which is the importance of monitoring. Because when I continuously monitor my model, I am very alerted, and I'm very, I can easily find the data shifts in population or condition prevalence, and I need to be able to adapt to how the world is developing and new diseases coming up and labels changing and even disease representations being changed. So in some cases, a specific condition that was represented in a way, the flu is the best example because each year the flu is represented a little bit differently. So one year the flu is cough and runny nose and stuff like that. And another year it's diarrhea and vomiting. So I need to be able to do this dynamic learning and continuous learning all the time to be able to continuously suffice this integrity and accuracy. Continuous learning is the key to doing this. I don't know if you've heard this term before, but if you have a model in the wild and you need to be able to adapt to changes of what's going on, you have to be on continuous learning all the time. And continuous learning is the only way that we can keep up with the business KPI, which is model accuracy. So there are a few things that that continuous learning must have before we decide to do it. So first of all, we need to have a need. Okay, we don't just decide one day, okay, my model is out for like half a year, I should train a new model, I should do continuous learning. If there's no need, if there's no alerting data shifts, or the KPI wasn't affected, or the model performance wasn't affected by the metrics that you set, or you don't see any insights from your monitoring metrics, why do it? It's just a waste of time and could just affect your model, and you would be overfitted to a specific population that looked at the app at a certain time. So the need is very, very important. And not less as important is the data. So even if you recognize that there's a need, you need to be able to learn something. So the data must be rich enough to represent what you're trying to learn. You need to have enough data to learn. You need to have enough data to evaluate after filtering and feature extraction and all those things. And last but not least, you need to be able to quickly and efficiently evaluate your model, because the key thing about continuous learning is that it needs to be fast. If you decide to train a new model and it will take you 4 months, you've lost your edge. In 4 months, everything would change. So everything needs to be quick. And evaluation is one of the main parts that takes the most time.
Like your ground truth, basically a majority vote of doctors?
Not exactly.
So what am I missing? What's the, like, is there a feedback loop? Like, how, I mean, how, okay, you got a diagnose from doctors, right?
Yeah.
So this is the ground truth. I mean, like,
yeah.
You're going back to the model and you say, okay, let's tag this sample, this patient.
Yeah.
That's what the doctors say.
Yeah.
The majority.
Mm-hmm.
But is there any like better evaluation? Like, I don't know, like asking the patient, you have an application. The patient, do you feel better? Do you have a running fever?
That's a good point.
Like there's Taito for children. I mean, you can.
Taito is something else. Taito is a physical exam. No, it's a good point. It's a good point. It's a good question, and this comes to outcome measurement, and this is a field that we are now getting into. For now, we have the labels that the doctor gave. We don't know if it really helped the patient. We are now collecting this data, so the next level of continuous learning would use that. But the way that we score ourselves is based on agreement. So it's kind of like majority vote, but we don't just take the the condition that was voted the most, we use other conditions as well. Sorry? All the time, yeah. Okay, so yeah. The app gives you a differential diagnosis. It tells you what you might have. If you go into the information pages for each diagnosis, you can, if you have one of the diagnoses is serious, you would get a red banner saying, this is a serious condition, you should consider going to the doctor. Even during the health dialogue, if you report a very serious symptom like head trauma or, I don't know, runny nose that is like very massive, we will give you an alert that you probably should seek medical care. But again, the app is not a medical device right now. So we can't tell you to go to a doctor. We give you information on what to watch out for. Even if you have the flu, we will tell you if you see that you are developing, I don't know, dizziness or having trouble breathing, you should seek medical attention. We're not actionable at the moment. The app is not a medical device. The doctors can give the prescription. We do have other models that I didn't present here, also data-driven, that are physician-facing, and they help them make medical decisions, inform medical decisions. Yeah. Have membership. We have, there's a few programs, okay, but the main programs are memberships. So you pay, I don't know, I think it's $10 a month, and you have access to doctors via the app all the time. You have one-time subscription where you can talk to a doctor just this once. We have various programs related to other very common issues like behavioral health and ED, erectile dysfunction, which are very common. And these are paying members that are rapidly going back to the app and having conversation with the model. And I don't know if I forgot to mention it or not, but we also collect the data of the chat between the user and the doctor. And this also goes as part of our continuous learning, because the doctor is asking questions, the patient is answering, so we can also learn new models or new representations from that. Okay, yeah, good. So basically, the bottom line is that our model gets better with every case. Every case that we collect, we can make our model better, we can learn, we can get new features, we can get new insights, and all these stuff. So what we basically created here is like a very high frequency, very efficient system to utilize the data, the interactions that we have between the patient and our AI, and between the doctor and our AI, and even between our doctor and the patient. And we can use this data collected to train new models all the time. And we can rapidly put them in production by using our evaluation framework, which is like very extensive and agreed upon, and everybody knows why it's good, and everybody understands it, everybody respects it. And then we move on to continuously monitoring our results, seeing the effect, understanding when we need to do something, and then just repeating this loop over and over again. And this is not just specifically for having a new diagnosis or improving a specific diagnosis. We improve with having new features, new symptoms coming to the world and being very, very common, like loss of taste and smell. Who knew? Who thought of it? And suddenly we have it all the time. So we need to be able to rapidly put it in. Maybe, you know, new representations of a disease, and we need to understand that it is rapidly changing. We need to put it, we need to learn it. Even understanding how to ask questions better. We asked a question, we had a specific phrasing on, do you have a headache? But we see that users don't really understand it. And the doctors, when they talk to the user, they ask something differently. We can learn these phrasing. We can change our phrasing in the way we ask questions. And this is what keeps us very accurate and high in demand, and just very, 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 very nice and happy place to work in. Yeah.
You said that you're not changing your model. You do not change the model for you don't put wild new models. Always.
No, we always put new models in the wild. Yeah.
But you said only if we find shifts in the data or that we find in a different way. So then we go back and we put another model.
So now it's the question was.
I mean, maybe you learn on the background the whole time, and then you have always a ready model to update your model.
So the question was, do we only update the model when we see a shift in the wild? The answer is no. We have some models that we know that the baseline that was initially launched from the first days of the company aren't good enough. They're not good. We have very low accuracy. The KPI is very affected by them. So if we don't have a shift, I mean, we are a lot of data scientists, so we're working all the time, but we will always try to improve even if there's not a shift. If we feel that this model is not good enough, that we have an accuracy of 82%, but we can reach to 93%, we will do it. We will continuously keep improving. And the main tool that helps us improve right now is the fact that we are actually using our own data and not an external data that was very, very biased and different from what we actually need in the wild. If there are any more questions, I'd be happy to answer. Yeah.
Partnership or how things like this start.
It was the question was how did it start? How did we get the data in the first place? And was it a partnership? Yeah, it was a partnership. Yeah. Okay. Yeah. Come work for us and I'll tell you.
But like you have to use something really explainable if you're really limited.
Yes, I mean, we don't have to use something that we don't have to use logistic regression just because it's highly explainable. We put an emphasis on explainability because part of this evaluation pipeline and part of the building was showing the physicians why a model is making a certain decision and why does it get it wrong, and explainability really helps. But we do have deep learning models in production. So we have everything. We do feature engineering, of course. I'm guessing not. I mean, the model it could go either way. We settle on a specific model, and now I can tell you that some projects are using more advanced models or more complex models, and the architecture keeps changing. And we also have this really nice game of inserting the domain knowledge into the architecture of the model, which really helps the results. Not in just rules like if, else, just really, really like connecting specific neurons and stuff like that. Mm-hmm. Yeah, that's a really good question. It's a really big problem in highly unbalanced data, specifically in medical data, where, as you mentioned, the question was, sorry, how do we handle like really rare cases where there's overlap between those conditions and other conditions? So what we actually have are different classifiers for very rare diseases. And the way that we present the results is slightly different because the output that we get from the classifier is different. The evaluation stays the same. So we try to represent even those very rare cases in the evaluation pipeline. And we still have those cases of full agreement, so we don't make those mistakes. But the presentation in the app is slightly different because it's like a different model. It depends. I mean, you could have a new disease that doesn't require a new feature, just uses the old features. If we need new features, we can, it could be like manually adding them. It could be something a little bit more complex where we kind of learn the new feature and then we, by feature engineering or whatever, infer the new feature. So it depends on the situation. Yes. This is why this is a business KPI. It wasn't a mess. It wasn't, we didn't give like a bladder infection for people complaining about ear stuff. This wasn't the case. But I mean, the model was, it was fine. It was okay. It didn't make horrible mistakes, but it wasn't like, it wasn't really to the point. We could give like very wide differential diagnosis just to not miss anything. And then we might, for some cases, be overconfident about some diagnosis, which is also not so good to be overconfident in the medical world. So but the first model wasn't terrible. It got us a lot of users. It was in production for a very, very long time, and people worked very, very hard on it. But it had a lot of assumptions and biases that we needed to tend to when we started working on the new age of models.
An example where your model recognizes the disease better than the doctor? Or is it the case? Happens a lot.
Well, there are some cases. Yeah, can I find an example of conditions where the model is better than the doctor? I don't want to, I need to be very careful here. We have some conditions that are very, very prevalent in a specific population where we noticed that the doctors having the chats with the patients are not giving the right diagnosis and sometimes giving not the best treatment. And now we have a system specifically aimed for that condition. And it gives the doctor like a special screen when we detect this condition. And this is where the doctor can be actionable and just close the case very, very fast and very, very accurately. And by this, we make the healthcare system better because we kind of like, you can think of it as like an intern, okay, in a hospital. The doctor gets the case and he thinks of something, and then the intern says, well, you know, maybe it's this. And then the doctor says, oh, you're right. So this is where we are better. It's always a combination of features.
That's what the doctors cannot always do.
Yes.
Yeah, that's right. Yeah.
Yeah. I didn't go into much to, the product is very wide, and one of the main things in the product is actually collecting the right data, asking the right questions. And I didn't talk about that part, but that's a whole world of the model that can, I mean, ask the right question and understand what the diagnosis and understand what will give me information and what will just confuse me and what is relevant and what is irrelevant. So it's a whole other.
What I missed sort of based on all the information you have, and now the doctor has. So including the question that have you been traveling and everything, and you and the doctor starts different. So it depends on a combination. I mean, or maybe you saw something repeatable.
It depends on a lot of things. Yeah. So sometimes we have a conversation that asks all the right questions, and then we look at the dialogue between the patient and the doctor, and we see the same questions, but the answers of the patient are suddenly different. So we don't know why this happened. We don't know why the user said yes to this and then no again when we chatted with the doctor. There's stuff that we can't really capture in the automatic dialogue, and the doctor can ask it more directly. So yeah, this is the doctor, when the patient moves on to the doctor sees the entire health dialogue. He sees everything that was going on, all the symptoms that the user reported, every symptom that he said yes to, what the classifier gave. This is all visible to the doctor, and then he can move on to make his decision. Either ask more questions or just make a decision based on what he sees. It's up to him, but the information is completely there. In a way, yeah. We are aiming to help the user. We can help the doctor by making his work easier, by giving him decision support, by presenting him with the community opinion of what should happen in a case like this, by giving recommendation of medication to treat specific things. And in the US, you not only have to keep in mind the type of medication, but also the pharmacy that this patient can go to any pharmacy, and not all pharmacies have all medications. So everything needs to get together in a data-driven system to give the doctor the best recommendation and the best all the information that he needs to make the prescription eventually. The diagnostic part is meant to show the doctor what we think they have and kind of serve as another opinion. Keep in mind, this is what we think. Do you agree? Yeah, it's a good question. It's very hard to measure. We have like cold measures, like how many users are onboarding, how many users start dialogues, how many users finish dialogue. We have ranking, so the users can give reviews and we can rank them. How many come back, how many recommend, what was the intake tool that they use, because we are advertising in a lot of different platforms and in the web to download the app, and within the app we have advertisement to other products that we are marketing. So basically it's like normal BI metrics and satisfaction by review, and that's basically it.
Do you have any benchmarks
for user satisfaction?
Yeah.
Not really, no. A lot of competitors.
Like benchmarking and get.
So the main number that apps in this domain usually use are number of users, number of repeating users, number of interactions. Yeah, it's business.
No, there's marketing and there's the domain.
Well, the domain is affected by the marketing. If we market to a specific population that, I don't know, doesn't have cell phones, it won't help us. The satisfaction would be, is affected by marketing. If we market a new tool, new behavioral health tool that we have in a population that doesn't show a lot of behavioral health issues, then we can't get high user satisfaction because it doesn't make sense. So it kind of depends one another. Marketing is good enough to know what they're doing, but
no, I mean, there's another company who spends like $1 billion on marketing, more than you, let's say more than you. So there's lots of more user interactions that are there, or there's a better UI, but you have more quality in your product, so you can affect, you can show your.
This is part of the things that we show in our marketing campaigns, how accurate we are, and how much we agree with the doctors when we give a prediction, how much you can rely on us. It's everything that we're exposing to the public. This is why accuracy is part of the KPI, because we are using it as an intake tool. We want to show that we are accurate. We know what we're doing. We know what we're saying. We're utilizing a lot of data to be better than just one doctor. Yeah.
This will be industry related. What is the ratio? Like what teams do you have, and what is the ratio? I don't know, research, development, what's the more need?
Specifically in the data science group or overall? So the data science group is huge. We are above 20 people. We have both data scientists and engineers. So we have data engineers and machine learning engineers. And we have analysts, and we work on products mainly. This is the main focus of our job, but we do have a lot of research-oriented activities. So we have journal clubs that require journal clubs. So we present articles from like recent work that could be impactful, that could be relevant. We do support personal initiatives of POCs or things that we want to try and look at. So this is a part of what we want the people in the group to do. And I mean,
it's mostly engineers or mostly researchers?
No, it's mostly researchers. We are mostly data scientists. More than half of the group are data scientists and analysts. The data engineers and ML engineers are, I don't want to say supporting effort because they are a crucial part of the team, but we are all together just.
And you have the MLOps we hear about?
We have MLOps, yes. Yeah. Thank you so much.